Hello, and welcome back to TechFix. Today, we're breaking down software operations on the all-new Volvo VNL, and more importantly, what's really happening when things don't go as planned. Because here's the reality. Most software problems aren't software problems, they're system problems. We're tackling this head-on today. That's right, we're going to talk about network health, data link diagnostics, product data offline conditions, mismatches, and one of the biggest differences we see in the field, locked versus blocked modules. We'll also touch on Software Center as the preferred tool for software operations. We'll go deeper into that in a future episode, and how tools like Impact and knowledge of version 4 electronics architecture help you see what the truck is actually doing. If you've ever felt like you're chasing the problem instead of solving it, this episode changes that. Let's get into it. Let's start with the big picture. Software operations are not the starting point. They're the result. They depend on everything underneath them being healthy. That means power and ground integrity. That means network communication. That also means understanding how the system is laid out before you touch anything. On the all-new Volvo VNL, the vehicle is built around communication, nodes, sub-hardware, data links, backbones, subnets. Everything is talking to something, and whenever one part of that system isn't right, the entire system feels it, including software operations. So before we even think about programming, we need to understand the system we're working on. Let's talk tools. Software Center is the preferred tool for software operations on this platform, and while we'll break that down in detail in future episodes, here's what matters right now. Consistency. Using the same tool, the same workflow, and the same process removes variables from the equation. Legacy trucks followed a different approach, and that worked for that product. However, on this platform, Software Center is part of the process. Stick with it. It keeps diagnostics clean, and it keeps case handling consistent. Now, before you test anything, you need to know where you are. That's where topology comes in. Using Impact, you can pull up vehicle chassis ID in function group 3 and immediately see how the network is structured in the Vehicle Electronics Overview system description. Before we go any further, let's talk terminology. A node is any device that branches off a CAN, Ethernet, or LIN bus, which is to say they can either be hardware or sub-hardware. Hardware is typically an ECU, but important to note, not all hardware has sub-hardware. Sub-hardware are nodes that are hierarchically structured under a hardware, typically a LIN child that belongs to an ECU parent. Nodes live on a data link. Version 4 electronics architecture has 2 backbones and several subnets. Additionally, a bunch of LIN buses and Ethernet as well. Now, let's talk about how you actually connect. On legacy trucks, the 16-pin breakout box gave you a consistent place to access the data link at the DLC connector. That was the standard. On newer platforms, it's different. The 16-pin connector is a stub node of ISO-CAN to the VMCU, an Ethernet connection to the instrument cluster. There is no connection to the J1939 at the DLC. It's important that you have the correct part number with the blue end for Ethernet communication. Failure to use the correct cable will cause issues with Ethernet node programming. That part number is 888-940-01. In a quick tip, the Vocom 2 configurator is a quick and effective way to ensure the vehicle is communicating on both the Ethernet and CAN bus at the data links, ensuring it has the proper voltage. What does this all mean? Well, now you need to connect at the most logical point in the harness based on where you're testing. There's no one-size-fits-all access point anymore. Where you connect matters because where you connect determines what signal you actually see, and if you're not in the right place, even a good reading can point you in the wrong direction. Also, the OBD is powered via 12 volts. The cab can lose 12 volts and still look operational. All 24-volt loads still work, but you won't be able to pull codes because the 16-pin isn't powered. You'll need to diagnose the loss of power. The 12-volt cab load starts at the BPMU. Something we're seeing a lot of right now are multimeter readings that look good but don't line up with what the truck is actually doing. This depends greatly on the make and model of the multimeter you're using. For example, most of the time the meter is set to min-max and it feels like you're capturing the full signal, but that's not what's really happening. In many cases, the meter is averaging parts of the waveform. So what you're seeing isn't wrong, it's just not complete. And that's where things start to drift. Because if you're not seeing the true highs and lows of the signal, you're not seeing the actual condition of the network. To capture that, you would need to use the peak function. That's what gives you the real min and max values of the waveform. Once you see that, everything starts to line up. This is also where connection point comes back into play. Right tool, right setting, right connection point. When those three things line up, your readings start matching reality, and that's when diagnostics gets faster. For a more detailed diagnostic evaluation, utilize an oscope. I'll tell you what, let's go take some measurements. When you're working with data links, there are a few core checks that always matter. For CAN, resistance, CAN high voltage, CAN low voltage. Always keep in mind that resistance must be checked with power off. The maintenance battery disconnect will be the best way to ensure that all modules are asleep. An awake CAN bus will show inconsistent resistance readings. For voltage, use a multimeter in peak mode to check CAN high and CAN low for proper voltage. When measuring between CAN high and ground, voltage should measure between 2.5 volts and 3.5 volts. When measuring between CAN low and ground, voltage should measure between 2.5 volts and 1.5 volts. With LIN treated as a complex input pin, DTC should trigger for open, short to ground, or short to power, and missing messages. Use basic electrical tests to troubleshoot. Additionally, pay attention to calibration routines in the diagnostic tool. If you miss a calibration, it may cause missing messages. For example, if a flex switch isn't calibrated, it could cause a missing message fault. These checks give you a clear picture of network health, and they're not just helpful, they're foundational. Because if communication isn't right, nothing else is going to behave the way you'd expect it to. Let's clear up one of the biggest sources of confusion we see in the field: locked versus blocked modules. A locked module is temporary. You'll see the padlock icon. Think of it like a book checked out from a library. Somebody has requested software for that module, and once it's done, the module becomes available again. In most cases, locked modules can be handled by the technician through CBR 2480 without the need for e-service. Now, blocked modules are different. A blocked module is indicated by a red circle and means something is preventing programming from moving forward. That could be something on the truck or something in central systems. Here's the key mindset shift. A blocked condition isn't something to push through. It's something to understand, because once you identify what's causing the block, the path forward becomes clear. And in some rare cases, forcing programming through a blocked condition can actually create more work than it solves. So instead of pushing, pause, understand it, fix it, and then move forward. Product data offline means the node isn't being recognized by the diagnostic tool. That could be an ECU or a LIN node. Most of the time, this comes back to power, ground, or data link communication. Sometimes you'll see one or two nodes offline. Other times, you'll see several. The key is understanding that in the context of the network. One or two nodes might point to a localized issue. Multiple nodes could indicate something affecting a larger portion of the network. And that's where topology comes back into play. Here's the big takeaway. If the node isn't communicating, there's nothing there to diagnose yet. No DTCs, no software, no replace hardware. Step one is always restoring communication. Then everything else follows. Once you confirm a node is offline, the next step is to verify the basics: voltage, ground, CAN resistance, CAN high, and CAN low voltage. If it's a LIN node, continuity and min-max voltage. These checks tell you whether the system can even support communication. From there, attempt a hard reset by disconnecting and reconnecting the component. Then, use standard electrical troubleshooting to find what's missing. And here's where you can make your life a whole lot easier. Document it. Fill out the worksheet. Attach it to the case. And include a screenshot of the control unit information screen. That shows exactly what you tested and exactly what the truck is reporting. When that information is there, support doesn't have to guess, and that means faster answers. Now, let's look at a slightly different condition: central data missing. In this case, the module is there, it's communicating, but Central Systems doesn't recognize it correctly. This isn't a communication issue, it's a synchronization issue, and the fix is usually straightforward. Run replace hardware, or use function 17903-3 to synchronize ECU data. You're simply aligning central systems with what's actually on the truck. Let's talk mismatches. In PTT, it's called a mismatch. In Workshop Toolbox, it's called a deviation. Same thing. These can happen for a few reasons: product data offline, component replaced without running replace hardware, or part number differences between the truck and central systems. Now here's where it gets important. Some mismatches are informational, others are blocking. An informational mismatch just needs to be synchronized. A blocking mismatch stops programming until the issue is resolved. So the goal isn't just to see the mismatch, it's to understand what type you're dealing with. First step, run replace hardware. A lot of the time, that brings everything back into sync. If it doesn't, now you're looking deeper. That could mean a blocking condition or a part that doesn't match the truck build. At that point, verify the part number against impact. Don't assume, confirm, because once you know that piece is correct, everything else becomes easier to narrow down. CBR 2451, Troubleshooting Mismatches, has been updated to help improve case quality and speed up resolution. And this is actually a big win for technicians, because it makes it easier to get faster answers. That includes using a worksheet that captures key diagnostic checks: power, ground, data link. And here's the habit that really makes the difference. Attach the worksheet and attach a screenshot of the control unit information screen. Now, support can see what you've tested and what the truck is reporting. No guessing, no back and forth, just faster progress. Better data in, better results out. At the end of the day, this comes down to approach. Don't start with software, start with the system. Check the network, check power and ground, understand topology, because once those are solid, everything else gets easier. You're not chasing problems anymore, you're solving them. On the all-new Volvo VNL, software operations depend on system health, network integrity, accurate inputs, and correct diagnostics. When you understand how those pieces work together, you stop guessing and you start diagnosing with intent. And when you diagnose with intent, you fix it right the first time. That's TechFix, and we'll catch you next time.